Right, so this is 7.1 continued. I want to specifically talk about empirical versus classical probability. So we have classical probability from the last video. Classical probability is from the text P of some event, which means the probability of some event, is equal to the number of possible outcomes in the event. We'll use that symbol for number. Possible outcomes in event over the number of outcomes in the sample space. Okay. Empirical probability whoops. To contrast with classical, so classical probability is like theoretical probability, the number of times that the number of ways something can happen divided by the total number of possibilities altogether. Empirical probability is going to be, it's almost like more experiment based. The number of times an event occurs, or the event, whatever event you're experimenting with, over the number of times the experiment is performed. Okay, the number of times the experiment is performed. Okay, so examples. Let's say, okay, I need a prop. Where is my... Okay, so I had to go find my set of dice because my girlfriend's cat took off with the bag of dice I have here, but I found it. Okay, so I have some dice, and let's say that I have a 12-sided dice. So this is a 12-sided die, or I guess I should say die when it's a singular. Dice is plural. Anyways, 12 sides. And I ask the question of landing, what is the probability of landing on a number less than 5 when rolling a 12-sided die? Okay. What is the probability of landing on a number less than 5 when rolling a 12-sided die? All right, and why did I pick a 12-sided die? You know, typically it would be a 6-sided, right? Well, I thought this was more interesting than a 6-sided die. All right, classical probability tells us what? Classical probability, so I'll say CP for classical probability, tells me that the probability of rolling less than a 5 is going to come from the number of possible outcomes, the number of possible ways that this can occur over the total number of outcomes in the sample space. So what do I need? To calculate classical probability, I need the sample space, and I need to know the number of things in the sample space. So my sample space is going to be the set of total possibilities, the total possibilities that can happen when rolling a 12-sided die. So last time, if you watched the 7.1 video, which you should watch that before you're watching this, we listed the sample space for a 6-sided die by literally drawing the picture. So here it is, the sample space for a 6-sided die, literally drawing pictures. Because the point is, why do we do this? The point is, the sample space is not necessarily a set of numbers. It's not like 1, 2, 3, 4, 5, 6. It's rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, or rolling a 6, right? Now, in this case, same thing, right? Rolling a 1, rolling a 2, all the way up to 12. But because drawing these little pentagons, 12 of them is going to be tedious, I hope you're okay with me just writing the numbers. I'm going to let the number 1 represent rolling a 1, okay? And the number 2 represent rolling a 2, which you're probably thinking like, yeah, it doesn't really matter too much. So I'm agreeing with you in saying that that is my sample space. Just got to keep in mind that it's not a set of numbers, it's a set of different possibilities for this die, rather. Okay, now I need the size of the sample space, right? So I need the sample space and I need size of sample space, but that's easy. If there's 12 items, it is 12, right? It needs size of sample space. So in other words, the cardinality of this set, since there's 1, 2, 3, there's 12 items, and the cardinality is 12. Okay. I also need the number of possible outcomes in the event. Need number of ways the event can happen. What's the event? The event is rolling something less than a 5. Let me write out that set. How can I roll something less than a 5? I can roll a 1, I can roll a 2, I can roll a 3, I can roll a 4. So each of these numbers represents rolling a 1, rolling a 2, rolling a 3, rolling a 4. That's the number of ways this event. So the event is landing on a number less than 5. That's the event. Oops. And how do I find the number of ways this event can happen? Well, I take the cardinality of this set, which is clearly 4. All right, so all that to say that my classical probability, which is supposed to be this divided by this, my classical probability is going to be, in this case, is going to be 4 out of 12. 1/3, or 33.3 repeating percent. 1/3 chance. 1/3 chance. Cool. That did not require any experimentation, right? That just comes from understanding how many different possibilities there are total, and then also understanding how many different ways there are to get something less than a 5. I could get this, a 1, I could get a 2, I could get a 3, or I could get a 4. But anything outside of that, like a 6 or a 10, is not going to fall into my event space. Now, let's talk about empirical probability. In fact, let's just... I'll leave it like that. Okay, so empirical probability now. And I'm going to get a fresh sheet. When you're asked to calculate a probability, more than likely the problem is talking about classical probability. You would only be asked to, if you're asked to calculate empirical probability, then you're being asked to do a bunch of experiments. So most textbook problems are going to be classical probability, but it's good to talk about empirical probability as well. So we need, what do we need? We need, for the denominator, we need number of times So I'm looking at this, right? Number of times. So you should have that written down, or you can look at it in the text as well in section 7.1. Number of times experiment is performed. Well, this is going to be up to me. And the experiment is rolling the dice. Rolling the die. Now, how many times should I do it? Right? Well, that's a good question, right? The more the better, right? But how about I say, just for the sake of what we're doing here, I'm going to say, I will roll the die. How many times do I want to roll it? 30 times. Yeah, so I'm going to do it a lot. Okay. I also need, so that's my denominator. I decide what that is. Now I also need the number of times the event happens, the event occurs. And the event, remember, is rolling a 1, 2, 3, or 4, rolling something less than a 5. All right, that's going to come from the experiment. So what I'm going to do is I'm going to keep track of these things by saying I'm going to make a little table. How do I want to say? I'll say event occurs on this side, so I'll keep track of how many times the event occurs on this side. And over here, event does not occur. So this would be like rolling a 5 or bigger. And I'll just do like tick marks. All right. So what I recommend now, since I'm actually about to do this, is I recommend muting your speakers because this is going to be loud. I thought about just pausing and doing it and then writing down the numbers, but I want you to see that I'm not just going to make this up, right? Okay, so here we go. So that did not work. That was a 6, 5, 4. Okay, another 4. Oop, 2. Okay. Okay. That's a 1. Okay, 6. Some of these rolls maybe are not very... That wasn't... Hang on. I'm not doing good rolls. Oh, that was a 1 again. All right. That's an 11. 3. 6. 4. Hang on, I'm losing track of how many I've done. That's 5, 10, 15. Okay. This is 20. 1, 22, 23, 24, 25, 26, 28, 29, no, 5, 10, 15, 20, 25, 28, I miscounted somehow, 29, and one last one, 30. Okay, that was 30 altogether. So, unmute your video, we're done with the experiment. So, the number of times the event occurred. Well, the event occurred is over here. That's 11 out of total number of times. So not the other column, but the total. So 5, 10, 15, 20, 25, 30, right? That's how many times I did the experiment. And what does that equal as a percentage? Oops. 36.6 repeating percent. I mean, that couldn't have gone really too much better, right? what is the point here? The point is, when you do your experiment enough, if you do it enough times, then these two probabilities should, where is it? Where's my, here it is. These two probabilities should perfectly match up, theoretically. So if I was to do like 300 rolls, then you would expect this number to get even closer to my theoretical or classical probability. Sometimes, you may hear me say theoretical probability. If I say that, I'm talking about classical probability, whereas empirical is like experimental. Experiment versus experimental versus theoretical. That's kind of what's happening here. So the higher the number of experiments, the closer this will get to this classical probability that we calculated here. And you may have seen that at the beginning, at one point, I had 4 on this side and 4 on that side, which means like 4 out of a total of 8, which is 50%, which is not a good estimate. In fact, like even at the beginning, there were so many on this side that I was beginning to think like, is something wrong with my die, right? Because it's like keeps landing, it's landing too much on 1, 2, 3, or 4. But as I did more numbers, you see, as I did more numbers, that it went from 50% and it started shrinking and getting closer to that 1/3 or 33-ish% that we expected. So this is the difference between classical and empirical probability. Calculating classical probability is all about identifying the size of sample and event space and then building a fraction out of them. No experiments needed. Empirical probability is all about the experiment. And then what's the connection between the two? What's the connection between the two? The connection is, let me put this back here. The connection between these two is that as the number of times you do the experiment goes higher and higher, that these two numbers should become equal. They will become equal as long as your, classical probability was calculated correctly and all that. Okay. Cool. That's it.